Hi, this is our distributed trading risk monitor. We built an event-driven microservices platform on AWS that processes financial transaction in real time through 8 independent services. The problem we are solving is a trading platform that has thousands of concurrent transactions. Each one needs fraud detection, risk evaluation, and compliance checking with audit logging and analytics. The catch is like if any of these checks are slow or crash, it cannot block the trader. That's the core problem, which is like speed versus safety. So we propose a solution. When a trader submits a transaction, the transaction service writes it to a DynamoDB, publishes to an SNS, and immediately returns a 202 accepted. The trader has to never wait. The SNS then fans out to that event to the per SQS queues, as you can see in the diagram, where every relevant service gets its own copy. A fraud, risk, and compliance each have their detailed queue for high priority transaction, and for analytics and or audit logging have their own queues, which receive all transactions regardless of priority. Each service processes independently, so if anyone crashes, the others keep running. Failed messages go to dead letter queues where the manual review service picks them up. The entire infrastructure is formed on Terraform, and which contains 12 modules covering VPC, ECS, Fargate, SNS, SQS, ALB, ECR, DynamoDB, S3, Redis, which is in two regions, and auto scaling and CloudWatch logs. So now Shloka will walk through the contributions.
Starting with the technology stack, we have all the 8 services which are written in Go, and they are all running on ECS Fargate. We are using SNS for event fanout, SQS for per service queues, and DynamoDB for transaction storage, Redis for real time states, S3 for audit logs, and CloudWatch for monitoring. My main contributions were the transaction service, the data layer, infrastructure components, and the load testing framework. So, the transaction service is the entry point for all the trades, and it accepts a post request which passes through the ALB, validates the payload, and writes the transaction to DynamoDB with a pending status, and then assigns a priority based on the transaction amount. So anything that is over $10,000 is set to high priority, over 50,000 is critical, and that publishes the event to the SNS with that priority metadata and returns 202 accepted. The entire round trip takes about 130 milliseconds under normal load. I've also built the manual review service, which consumes from the dead letter queues. When any service fails to process a message after 3 retries, the message lands in the DL queue, and the manual review picks it up, writes it to DynamoDB as pending review, and then publishes an alert. On the infrastructure side, I set up DynamoDB for transaction records with status tracking, S3 buckets for immutable audit logs, and Elasticache Redis cluster that the risk monitor uses for tracking daily exposure. I configured ECS auto scaling policies that scale each service based on its individual queue depth. When messages pile up, more tasks spin up automatically. And I also created the CloudWatch dashboard showing real time queue depths, processing latency, error rates, and ECS task counts. For load testing, I built all the locust scripts, the base trader simulation, the stage load test for finding the breaking point, and audit test for data integrity. I also wrote the reconciliation script that cross checks every submitted transaction against the DynamoDB S3 audit logs and all the DLQ depths. Now, Dhyan will cover the high priority services.
Um, So my work focused on the core processing services, the ones which handle the critical safety checks on every high priority transaction. First, the shared SQS consumer library. Each service in our system uses this library to poll messages from its queue. It handles long polling, automatic message deletion, and successful processing, error handling with all the retries and graceful shutdown with that. Writing this once and reusing it all across eight queues would be would be an would be consistent with that. I also define the event JSON schemas, the structs, and then serve them as a contract between the services. Transaction, event, fraud, alert, risk, breach, compliance violation. Every services serializes and deserializes using this shared types. The fraud detection service consumes from its dedicated fraud queue. It checks each transaction against fraud patterns and stored in DynamoDB, which are high value and rest all. Then so when a fraud is detected, it updates the transaction status in DynamoDB to a flagged with a reason and publishes a fraud alert event to SNS. The risk monitor is the most technically interesting service. It tracks cumulative daily spending per user using Redis. The key feature is support for three sync modes: single write to the Redis, local for independent regions, and dual write for synchronous cross region replication. It also supports two check modes: atomic using Redis increment by float, where the increment and read happen in one operation with no race window, and atomic using get and then set with a deliberate race condition for the experiment. When daily exposure exceeds the $50,000 limit, it blocks the transaction and publishes a risk breach event. The compliance service checks against regulatory rules, which are blocked user list, blocked merchant list, and transaction amount thresholds like $10,000 reporting requirement. When a violation is found, it updates DynamoDB and it publishes a compliance violence event. The alert service sits at the end of the alert pipeline. It subscribes to both of the fraud alert and risk bridge SNS topics through its own queue and simulates sending a notification when critical events are detached. So now Vidit will explain the experiment.
Okay, so let me walk through my contributions first, and then I will start with all the experiments we have done. In total, we have done 5 experiments. So basically, like I built the entire Terraform infrastructure for the whole project, where it had 12 modules, where covering VPC, ECS, Fargate, SNS, SQS, ALB, ECR, DynamoDB, S3, Redis in 2 regions, auto scaling, CloudWatch dashboards, and ECS service definitions. The most important architectural decision which was taken by me was the per service queue design, which I took after like one iteration of the project, because if it is not a dedicated queue, then it will just consume the first service will consume the message and all services won't get the message. So that's why the per service queue design was implemented instead of shared queues. So like SNS fans out every transaction to dedicated queues, so each service gets its own copy. I also set up Redis in 2 AWS regions for the cap theorem experiment. For services, I built the analytics and the audit logging services. So basically, the analytics services pushes the custom CloudWatch metrics to show us different metrics related to latency, throughput, queue status, DLQs, and different things. And also for like the audit logging services, which batches the transaction into in memory and writes them as an immutable JSON when one batch is completed to the S3. So basically, in a trading company, the audit logging is very important. That even if the transaction is stored in a database, we still need to store it in a logs file. So basically, it batches the whole thing and stores in a log file. Also, I created the chaos engineering dashboard, which was basically inspired by Netflix. The chaos engineering dashboard was built with React UI in the front end and Fast API as the back end, like with 4 services tab, where we can live monitor all the services that we have. We can kill some services, add delay to services, and also we can observe how many transactions are going. And there was a new tab added to that dashboard, which was the upload Excel tag, like we can upload a whole Excel file with 100 transactions together to run those pipeline transactions one together. So basically, also I made some automation scripts like the Docker scripts for all the services and their build scripts also. So now let's start with the experiments. So first experiment, it was the extreme load test where we progressively ramped from 100 users to 3000 concurrent users across 5 stages over 17 minutes of time. At 100 users, the system was properly stable and about 105 second request per second, where the response time was 500 milliseconds and at zero failures. So at 500 users, the response time climbed to 3 seconds, but still no failures. And the breaking point here we got was the 1,000 users, where we had some of the 502 bad gateway errors because like EC2 instances were scaling, and the total request we tried were 2,97,660 requests, where 34,811 failures. So the key finding was 95% of the failures were 502 from the transaction service. So SNS, SQS, and all consumer services were never the bottleneck. So the event-driven architecture worked exactly as designed. The HTTP entry point broke, not the queue infrastructure. So this was the bottleneck we came to know, and then we increased some instances. Like we increased from 5 to 10 instances for auto scaling. Then the second experiment was the cascading failure, zero trader impact. So basically, the cascading failure is we ran 200 concurrent user and killed all three high priority services, that is the fraud, risk, and compliance together using the chaos dashboard, which disables the auto scaling also and sets the desired count to zero. So the result was that all the high priority queues have 3,13,846 transactions with exactly zero failures. So the traders experienced absolutely no impact when the three critical services were dead for 5 minutes. Messages accumulated in the queues, and when the services were turned on again, the messages were consumed like a normal service is consuming. So this was basically the aim of the chaos engineering dashboard, which we implemented to kill services and still try the fault tolerance of the system. Now experiment 3 and 4, Dhyan will continue.
So in experiment 3, it was atomic versus non-atomic risk limits, in which like what happens when multiple service instances concurrently update the same value in Redis without atomic operations. We set the daily limit to 50,000 and send concurrent transactions of $10,000 each from 100 locust users, all for the same user. With atomic mode using Redis increment by float, the result was mathematically precise, where exactly 5 transactions allowed. So in around 16,000 something blocked. The CloudWatch logs show previous total incrementing sequentially 0, 10,000, 20,000, 30,000, 40,000, and so on. Every transaction saw a unique value. Then we switch to a non-atomic mode, get the current value, sleep 10 milliseconds, and then set the new value with concurrent go routines processing messages in parallel. The CloudWatch log tells the story. Multiple entries at the exact same millisecond, all showing the same stale previous total value. Multiple go routines read 0, all computed 10,000 is under the limit, all allowed the transaction through all wrote 10,000. The $50,000 limit was violated. Then this is the classic read modify race condition. With the takeaway for this atomic operations are not optional or shared for a shared state in distributed system. Redis latency was around 780 microseconds, and the atomic overhead is negligible compared to the correctness if it guarantees. So for the fourth experiment, it was cross-region Redis, in which we are testing the Cape theorem. Basically, we deployed Redis clusters in two AWS regions, US West 2 and East 1. And tested 3 configurations, in which one was single region mode, where all writes go to one Redis in the US West 2 with a strong consistency. But if the region goes down, risk monitoring stops. Average response time was 1000 milliseconds. So for that another test like independent mode, each region has its own redis and writes only locally. Both regions are fast and available with around 1000 millisecond but a user in a but a user trading in both regions simultaneously can exceed the daily limit because neither Redis sees the other's rights. So this is available and partition choice. And the another test was like dual write mode, in where every increment by float synchronously replicates to both Redis clusters. The limit is enforced accurately across the regions with 1000 milliseconds average. The cost is a hard dependency on inter-region connectivity. So if the link breaks, risk checks blocks entirely. This directly demonstrates the Cape theorem. The system cannot simultaneously be available, consistent and partition tolerant. For financial trading, the choice is CP, better to halt trading and then allow risk violation. So their next experiment will be explained by Shloka.
So the experiment 5, it is related to data integrity audit. The main question here is, in a system that is using SQS, that is at least once delivery, does every accepted transaction actually make it through the full pipeline? Are there any missing records or any duplicates? Any messages that are stuck in dead letter queues? So, what we did was we submitted approximately 9,976 sequential transactions with unique user IDs through 50 concurrent locust users. Every 202 accepted response was then logged to a CSV file with the transaction ID and a timestamp. After all the queues were drained, the reconciliation script cross checked every single transaction against the DynamoDB, counted S3 audit log objects, and checked all 5 DLQ tips and scanned for duplicate transaction IDs. The result was that after perfect reconciliation, 9976 were submitted and 9976 records were found in DynamoDB, 0 missing, 0 duplicates, and 0 DLQ messages. 102 S3 audit logs audit objects confirmed that the audit logging batches flushed successfully. The reason for this perfect result is that the transaction service writes to DynamoDB synchronously before returning a 202 accepted. A transaction is never acknowledged to the trader without being persisted first. At 120 requests per second, SQS at least once delivery produced no observable duplicates. But the limitation is that this was moderate load under extreme load with service crashes during at least once delivery could produce duplicates, and audit logging batch flush is vulnerable to data loss if a task is killed mid-batch. To summarize, across all 5 experiments, scalability has a measurable ceiling at the HTTP entry point, not the queue infrastructure. Fault isolation works with zero trader impact, even with 3 services dead. Atomic operations are essential since non-atomic access lets race conditions, violate safety limits. Data integrity is achievable with synchronous persistence before acknowledgement, and the CAP theorem is a real constraint for financial systems. So, in this case, consistency wins over availability. So, these are all the experiments that we went through. From here on, I would like Vidit to show a demo of the project.
So this is basically the the chaos engineering dashboard that we made. So basically, we have all the services listed here. That is the transaction, fraud detection, risk monitor, compliance, analytics, audit logging, alert, and manual review. So manual review is currently not running because whenever it gets a message in the DLQ, then only it's turned on, or else it's totally off. So basically, this all are running with one task right now. But if the load increases, if the queue is full, then it will auto scale automatically. So basically, this is the observability tab where we can see the transactions done today. These are the flagged number of transactions. So this is the error rate according to the flagged number of transactions. And also we have the transaction explorer where we have all the transactions that we have done the latest 100 we can explore here. And so this is Barabar. So basically, we can just upload this file here and we can submit this transaction. So we can see that we are getting all success responses, and the trader don't have to wait for the transaction to get through six different microservices. And we can also see here that the transactions are coming in, and so observability can see that transactions are coming 13 per minute. Like it's it is basically we are using the AWS API here, Boto3 client, to update the dashboard. And there is a transaction explorer that can show the currently the transaction going on. So so this is one API that so this is the flow of our project. So thank you. And this was the trading risk monitor that we developed.